So solutions near a singular point. So earlier, I showed you solutions near ordinary point. Now, what about the singular points? So given the form, this one I have to read it again. I've read this to you last time. X equals x sub 0 is a singular point when b of x sub 0 is equal to 0. So that means if there is a first term that's being multiplied to y double prime, or the highest order that you have here, and then that term becomes 0, the highest order will no longer be the highest order present, right? So what's the transformation? Given the general form here on top, divide everything by b sub 0 x. So you'll have simply y double prime plus pxy prime plus qxy. It's similar to how we simplify the differential equations in your Cal Eng 3. So here, what is px? Px would be b sub 1x all over b sub 0x. And then q of x will be the multiplier or the coefficient here divided by the coefficient of the leading term. So what are the conditions? If no x minus x sub 0 factor in the denominator of px has a power of greater than 1, and then if no factor in qx greater than 2, so that means it's going to be singular point. For example, in here, you're given something like this. So what I would want to do is I'd leave y double prime as is, and then I'd divide everything by the leading coefficients. It so happens it's just not just a numerical coefficient. The coefficient contains an x. So let's divide everything. So here the x and the 3, it becomes an x squared at the bottom. The x minus 4 cancels out, and x squared plus 1 remains. For the q, the x cancels, and then what remains here is x equals x minus 8, so on. So what you'll look at this is here, x equals 0. According to this, no factor greater than 1. So is the factor of 0 greater than 1? Yes, because it's squared. So that means it already failed the condition. Kasi if the factor is less than 1 or only 1, it's an ordinary point. But if the factor is greater than 1 already, it's already a singular point. So here, it failed. For q, 0 is x squared. According to q, denominator greater than 2. So here, the cutoff is 1. The cutoff for q is 2. Since it's squared, the cutoff is 2. It's okay. It passed. Okay, I'll go to the remarks later on. Plus and minus I. You know that the plus and minus I is from x squared plus 1. And it appeared only once. So that means it passed P. For Q, it also is the power of 1. It passed Q. For 4, 4 is here. It does not appear in the denominator. According to the test, it should be not higher than 1. So 0 is not higher than 1. It passed the test. In here, should not be higher than 2. 1 is not higher than 2. It passed the test. Now there's another point. X equals 8. X equals 8 is not found in the denominator. So that means it's simply an ordinary point. For those that pass check mark in both P and Q, this is what you call regular singular points. Those that did not pass, this is what you call an irregular singular point. So how do we solve regular singular points? Basically, similar to how we solve the ordinary point. The only difference is that we have, instead of just n, it becomes n plus r1, n plus r2. And then there are actually two coefficients, a sub n and b sub n. I'll teach you later on why. So Solutions near a regular singular point or near an RSP where the difference of the roots of the initial equation is non-integral, the initial equation can be determined when n equals 0. So those R1 and R2 that you see are actually what you call the roots of the initial equation. So what's that? You know just by looking that there is another variable beside y double prime. So that means this one would have a singular point, not just an ordinary point. What's the singular point? What will make the y double prime 0 if x is 0? So that means 0 is a regular singular point. How? What? Let's just try to divide 3 over 4x. The other one's also 3 over 4x. Now, in here, for p, is the power of x equals 0 greater than 1? No, so that means it passed. Here, the cutoff is greater than 2. So it's still passing because it's still x equals 0 is to the power of 1 only. So x equals 0 is what you call a regular singular point. Okay? So let's write the solutions. For the solutions here, as I said, instead of just x to the n, x to the n plus r. So you bring that down, a sub n, x to the n plus r minus 1, and then bring those down, x to the n plus r minus 2. And then we plug these in that. After plugging in, what you'll obtain is this. So the first thing is we evaluate this one at n equals 0, similar to how we evaluate the others. We evaluate at n equals 0, n equals 1, n equals 2, and so on. But in here, the main difference is that when we evaluate this at n equals 0, you'll be able to come up with r. You'll be left with r. And then the r that you are able to solve for will be the roots of your initial equations. Okay? R equals 0 and R equals 1/4. So let's try solving. I'll show you how to solve. Using the top right as your guide, summation from n equals 0 to infinity of 4 n plus r, n plus r minus 1, an. Instead of x to the n plus r minus 2, there is an x here. So that means this is x to the n plus r minus 1 only. And then 0 to infinity of 3 n plus r an x to the n plus r minus 1. And then lastly, 3 again, an x to the n plus r equals 0. So again, our target is to have the same powers. The lowest powers that you see at the moment is x to the n plus r minus 1. So this is our goal. So that means this one, we need to change the third. The third term can be from 1 to infinity of 3, a sub n minus 1, it's the n plus r minus 1. And then let's just combine the two because they have the same powers of x. 4n plus r n plus. So here, let's just factor out n plus r first. I'm left with 4n plus 4r minus 4 plus 3 a sub n x to the n plus r minus 1 plus this term. So 4n plus 4r minus 1. So here, n plus r, 4n plus 4r minus 1. All right. So this one will be that one. Since both of them are x raised to n plus r minus 1, we can already solve for the roots of the initial equation. Evaluate at n equals 0. So that means at n equals 0, 0 plus r, 0 plus 4r minus 1, and then a sub 0 is 0. So you're left with r, 4r minus 1, a sub 0 is 0. Take note that r can be equal to 0. 4r minus 1 can be equal to 0. So here r can be equal to 1/4. So a, if any of them can be equal to 0, a sub 0 is now an arbitrary term. So this one's the roots of the initial equation are 0 and 1/4. So let's just finish this. We have two roots. So r equals 0, the first root. Let's go back. What's the equation? Let's simplify this one. When r equals 0, this becomes n for n minus 1 because r equals 0. So n n x to the r equals 0, it's simply n minus 1 plus the summation n equals 0 to infinity of 3 n minus 1 x to the n minus 1 equals 0. So similar to how we solved before, when n equals 0, oh, both are 0, right? So unlike before, sorry, this is n equals 1. Sorry for that. So when n equals 0, you can say 0, -1, a sub 0 is 0. So we're correct. A sub 0 is arbitrary. Now, when n is 1, both will be activated. So I can say that when n is greater than or equal to 1, I'll have n for n minus 1, a sub n plus 3, a sub n minus 1 is 0. So here, a sub n is -3 over n for n minus 1, a sub n minus 1. So that means this is already our recursive relation. So some of you will ask, why is it only one constant, unlike before we have a sub 0, a sub 1, a sub 2, something like that? Because it does not repeat like you notice from here, n is 0 and then immediately it's n equals 1. So if I write what we were doing earlier, this is I, this is n, and this is a sub 0. So some of you again will ask, why is it I, n, and a sub 0 only, nothing more? Because there's nothing more to write. So when I have the first iteration, n will be equal to 1 as well because we already finished with n equals 0. When k equals 2, n will be equal to 2 as well. When k equals 3, n will be equal to 3 as well. So let's try. When n equals 1, a1, -3, 1, 4 times 1 is 4, minus 1 is 3, a sub 0. With a equals 2, that's going to be -3, 2, and then 2 times 4, 8 minus 1, 7, times a sub 1. But a sub 1 is -3, 1, 3, a sub 0, right? And then here, a sub 3 is -3. 3 times 4, 12 minus 1 is 11. Times, let's just copy the top. 1, 3, a sub 0, and so on. So if I am to write term, first, the relationship between n and k, n is equal to k. So that means this one is simply a sub n. There's no need to write k anymore because I only write k in here as examples here because this one has more than one term. But if the number of iterations is the same as the number of terms, there's actually no need to write the term k. We can just deal with letter n. Here, I can just write n since n is equal to k. So the negative sign appears that number of times. So -1 to the n. And then the 3 appears that many number of times. I can say 3 to the n. You will notice that at the bottom, what do you have? You have an n factorial because 3 to 1. And then there's 3 times 7 times 11. How do you write that? If you want, you can say, um, how do you write 3 times 7 times 11? That can be written as 3k, I know, 3n minus 1, right? Or if you want, you can write it like this first. 3, 7, 11, up until 4n minus 1. And then all of them end with a sub 0. So here, we can say that y is y sub 1 plus y sub 2. Why y sub 1 plus y sub 2? Because take note, there are, again, two terms. This one for initial equation root 0. Here, initial equation root 1/4. So for our y1, we can see that the answer is a sub 0 plus our a sub 1 is already here. I can say n equals 1 to infinity of -1 raised to n, 3 raised to n all over. You have n factorial. And then this one, instead of this, as I said, if you want to make it pi notation, you can make it pi from k equals 1 to n. Because again, for pi, we have to create another variable for k minus 1, a sub 0, x to the n. So this is only for y sub 1. By the way, I forgot to close this. There. Now, so let us solve the second solution. So in order to solve for y2, let's use r is 1/4, which is the second root of the initial equation. So when r is equal to 1/4, referring back to this equation here that we were able to simplify, summation when n equals 0 to infinity of, remember that this is n plus r, 4n plus 4r minus 1. So n plus r gives us n plus 1/4, 4n plus 4r, so 4n plus 4r minus 1. And then, as opposed to using a sub n, let's just use b sub n in here because we've already used a sub n in the previous initial root. This is x to the n plus r minus 1 plus the summation from n equals 0 to infinity. I think it's n equals 1 plus the summation from n equals, let's refer to this, 1 to infinity of 3a sub n minus 1 x to the n plus r minus 1. So 3. Instead of a, again, we use b. And then this is n minus 1 x to the n plus r minus 1 equals 0. So let's just try to simplify this one. 0 to infinity of n plus 1/4. This is simply 4n. This is bn x to the n minus 3/4 plus this one is n equals 1 to infinity of 3 b sub n minus 1 x to the, sorry, x raised to n minus 3/4 is equal to 0. So now that this is simplified, actually here, you can still simplify this with that becomes 4n plus 1 multiplied by n. So I place the 4 in the front. So here, let's answer. When n equals 0, what I'll have is 1, 0, b sub 0 is 0 because the second part of the equation still will not activate. So I can say for this to be 0, there's already a 0. B sub 0 is arbitrary. And then when n is greater than or equal to 1, both summations will activate. So this one will then be 4n plus 1 n bn plus 3 bn minus 1 is 0, or b sub n is simply negative 3 over 4n plus 1 multiplied by n b of n minus 1. So this now is what you call your recursive relation. And then again, similar to what we did in front, let's just write here, instead of I, let's just write k, and then our n, and then our b sub 0, because there's only one arbitrary constant, b sub 0. So when k equals 1, n is also equal to 1, b sub 1 is negative 3 over 5 times 1, b sub 0. When k equals 2, n is 2, b sub 2 is negative 3, 9 times 2. B1. So let's just expand this. 5, 1, B sub 0. And then lastly, when k equals 3, n equals 3, you have B3. That's negative 3 over 13 times 3 multiplied by negative 3, 9 times 2, negative 3, 5 times 1, B sub 0. And this one actually is B sub n negative appearing that many number of times, n times, 3 appearing n times as well. And then what you'll notice is that 1, 2, 3, there's n factorial, but there's 5, 9, 15. So let's just write that 5 times 9 times 15. And then that is 4n plus 1. All of them with b sub 0. Or if you want to simplify this, that can be rewritten as bn negative 1 raised to n, 3 raised to n factorial, and then pi from k equals 1 to n of 4k plus 1 b sub 0. So now that we have this, we can write our y sub 2. Our solution now will be y2 is do x, supposedly it's just x plus n, so 0 plus 1/4 plus the summation n equals 1 to infinity of negative 1 raised to n, 3 raised to n, this is n factorial, and then the pi notation from k equals 1 to n of 4k plus 1, and then this one is b sub 0 x raised to n plus 1/4. And do take note that eventually y is y sub 1 plus y sub 2. Again, your y sub 1 is this one, and then this is your y sub 2. So maybe we can rewrite that. So a sub 0, let's just factor out a sub 0. It's going to be 1 plus the summation from n equals 1 to infinity of negative 1 to the n, 3 to the n over n factorial k equals 1 to the n of 4k minus 1. And then here you have x sub n, x to the n. And then here, if I factor out b sub 0, this would be x to the 1/4 plus the summation from n equals 1 to infinity of negative 1 raised to n, 3 to the n factorial, I from k equals 1 to n of 4k plus 1 x to the n plus 1/4. So that means this one is your solution to your differential equation.